the regular NMR setup, and over here we have your sample that will be inside the sample tube. Please forgive my drawing, I know it's very fine, just like me. You have the sample tube here, you have a magnetic controller, and you have a magnetic field which you use like induce the current, the frequencies. Then you have a detector, you have a transmitter and a recorder, and it gives you a spectrum at the end of the day. Just like you should all know that all spectroscopic or spectrometric procedure should give you a spectrum. NMR will give you an NMR spectrum. The MS, that is mass spectrometry, will give you an MS spectrum. So for this, we'll be dealing with NMR spectrum. So now what happens over here is that the sample is inside this tube, your unknown sample. Or as a forensic pathologist, you have this sample that somebody killed somebody and you really want to know what a particular element is or what a particular substance. You want to know the structure and you've tried everything and it's not just working. You can bring this to the NMR machine. You put it in here, and then now what do? You add or you introduce a magnetic field. And I want to bring us to an equation. It's not a common equation, but it's an equation that shows us the relationship between the magnetic field and frequency. So this is the equation here. It's the regular equation, the regular Planck's E is equal to MC equation. But then it has been derived to give us this. Here you have delta E, which is your change in energy. You have your gamma sign, and this is what they call the gyromagnetic ratio. You have the H, which is the Planck's constant, and you have the H naught, which is the magnetic field. So there's a relationship between the H naught, which is the magnetic field, and your frequency. So as your frequency increases, or as your magnetic field increases, also your frequency increases. So they are in a direct proportional relationship. Do you guys understand it? So if you increase your magnetic field from 5 to 10, likewise the frequency should also increase from the initial number to a higher number. So with this, we can leverage on that and carry out the NMR techniques. So now, usually the NMR spectrum will be producing a graph of a spectrum with the magnetic field on the x-axis, either the magnetic field or the frequencies on the x-axis, and then on the y-axis you'll be having your peaks that have different meanings. So now you have the peaks on the y-axis, then you have your magnetic field or your frequency on the x-axis. I will note that, and then you see it. I will make sure to note that so you can see that you know what each part of the NMR spectrum means. So with this, now this equation helps to let us know that for every increase in your magnetic field, your frequency increases. So with this, let's get down to business. You introduce your sample into the sample tube, and then you start to increase the magnetic field. So you start from the smallest one. You start 0, 20, 30. So as you are increasing the field, what happens now at atomic level is that, just like you said, when a magnetic field comes closer to the atom of the element, the electrons at the atomos shell, they are the gatesmen. They are the people that are set to safeguard the proton. But your target, just like from the word nuclear magnetic resonance, your target is where? The nucleus. You are trying to get through to enter the nucleus. So what do? You need to what? You need to disarm those people at the edges. So what do now do? Use those your fields. So now, if there are a lot of electrons, your electrons will do the work of covering the nucleus very well. But if there are few electrons, it will be easier for you to shield them. So a lot of electrons shield the nucleus. Very few electrons shield the nucleus. So now, based on the particular structure of that compound, there are a lot of factors that can shield or shield the nucleus. Based on that particular structure now, you can now decipher the structure where it will peak at the record at the end of the day. But usually it's your sample. You add, apart from a sample, there's something else you had to add. It acts like an internal standard. In analytical chemistry, you add internal standard to help to remove errors that might arise from the matrix itself. So now, likewise here too, you have to add an internal standard, and that internal standard in this case is what they call tetramethylsilane. You have to put tetramethylsilane inside your mixture for your sample. So just like we said, after you have introduced your sample, which is mixed with your TMS, your internal standard, into your NMR setup, you said that you need to introduce your magnetic field or your frequency, and this magnetic field will help to either shield, like it can mean if the electrons are shielded or they're shielded, and if that wherever means they are in, your target is the protons. So the electrons which probably were shielded become shielded based on the frequency they are introducing inside, and then your protons in that particular sample of interest will begin to resonate at the frequency of your introduced energy or your introduced magnetic field or frequency. Once they begin to resonate at the same frequency, they begin to give you different peaks in your endpoint. But for now, we'd like to talk about the NMR like on the spectrum. We'd like to talk about the upfield and we'd like to talk about the downfield. First of all, when you say downfield, from the word down means that it's going down the drain. But now in NMR, when something is it is going in the downfield direction, it means that there is the shielding inside. It means that the electrons that you were supposed to cover the protons are now removed. So the protons are a bit naked. They are now deshielded. Like their shield has been removed. Just like how a soldier can lose his armor and then he becomes shielded and is open to any manner of attacks from the enemy. That is how the protons too will now be open to all manner of frequency interactions with the external magnetic field. And once you have something like that, you see that it is deshielded. And so once you are having a shielded values are normally supposed to be going towards like in downward arrangement, like 10, 9, 8, 7. But in NMR, you go upward. So that's like a paradox. In NMR, when something is downfield, it is deshielded. Okay, when something is deshielded, it goes downfield. But in going up downfield, the numerical parameter that is given to it is an increasing numerical parameter. Should you get this? So if something is downfield, it will be going it will be going towards 11, 12, 13 on the NMR scale. When from the word downfield should be going down. In this case, the numerical number you are giving, the numerical value you are giving it is high. Then if something is shielded, it is well covered. There is adequate amount of electrons that is covering it, like CMS, our internal standard of interest now. When it is well shielded, it will now go upfield, and then the numerical value you'll be attaching to it will be a very low value, which will be like 0. So you get it. The shieldedness, go downfield. Numerical value, a high number. Shieldedness, go upfield. The numerical value, a very low number. So in like a number line, in your number line, when you be going from 0 to 10, that 0 will now mean upfield, and then 10 will now mean downfield. I hope you are clear with this. So moving on now, let's talk about the factors that can affect NMR spectrum. And I can tell you that these factors arise from your sample of interest, that is the internal structure of your sample of interest, or even environmental factors, that is the metric factors, like where the type of solution that you deserve a sample in, or other factors like you get how concentrated your sample is and other things. So the first thing we have here is hydrogen bonding. Hydrogen bonding now, I would say that it's an environmental factor. It's more of an environmental factor than an intrinsic. So it's more of an extrinsic factor than an intrinsic factor. It means that in this case, hydrogen bonding affects this particular NMR spectrum, because if your sample is a concentrated sample, there will be risk or there will be high possibilities of having hydrogen bonds everywhere. Maybe your sample is dissolved in an alcoholic solvent that has an OH structure. There will be little hydrogen mixings here and there, and these hydrogen bondings can cause a deshielding effect, because a bond is formed between what? The electrons. So if the electrons that were supposed to be covering the protons now leave the work you send them to go and do, and they start to be bonding up and down, they get distracted, the proton of interest will be opened, and then your external frequency, your external magnetic field can now begin to resonate with your what? Your proton of what? Your interest. So that is why we say that usually in concentration solutions have lower, they go more downfield than dilute solutions, which go more upfield, because in concentration solutions there's a high risk of hydrogen bonds all around in your sample, especially if your sample has this sulfur group, the oxygen group, and the nitrogen group, and then it probably has hydrogen atoms in different locations. Once there is this S, there's an O, there's an N, there's a high risk of hydrogen bonding that can occur, and this hydrogen bonds is higher in concentrated solutions. Take note of this. Hydrogen bonds is higher in concentrated solutions, and due to this, it can make the sample to resonate at a much lower at a much higher frequency, which is now the shielding effect. Then also you have what they call unsaturation. This one is more like an intrinsic property of your sample. If your sample is unsaturated, so it could be double bonded, it could be triple bonded, or it could be aromatic. Double bonded like the alkenes, triple bonded like the alkynes, and even aromatic, that is the localized double bonds within a particular ring. That is the aromatic structure. Conjugated ones. So if it is unsaturated now, how unsaturation can affect the NMR spectrum is that usually the particular energy field that you're introducing, a magnetic field that you're introducing, it has its own particular direction it moves in. But usually when you introduce that electric field, the direction of your magnetic field that you bring in and the direction of those unsaturated, those pi bonds, they are not in the same direction. They are in like an 90-degree direction. One is going vertically, the other person is going horizontally. So I'm going to give you the structure like this now. So you have your double bond like this, and then your external magnetic field like this. This one goes in this direction, then you have your pi bonds here going in this direction. Because they're not going in the same direction and they're opposite sided now, because opposite sides obviously attract. Because they are going in opposite directions, the pi electrons will leave their position and they start to gain interest in the new magnetic field that you have brought in. And once they start to gain interest in the new magnetic field, like they are acting in opposite directions, it will make the protons to become deshielded. They will leave their primary place of assignment, and then they will not be picking at a much higher frequency. That's the protons itself now will be picking at a much higher frequency, because the electrons of interest are now attracted to, because they're opposite sided, they are horizontally at angle 90 to the electric field. It will make them now, they will leave their place of primary assignment and get interested in your external magnetic field, leaving the protons open for resonance to occur. So usually most unsaturated compounds like the alkynes, and the benzene rings and aromatics, we peak at a much higher frequency. We peak at a downfield effect because of this effect of unsaturation. So I'm moving on to anisotropy. Is just what is like the whole point of unsaturation is defined under anisotropy. So instead of you saying unsaturation, you could also say anisotropy. Anisotropy occurs for all forms of like unsaturated compounds. Moving on, next thing we have is temperature. Likewise, just like in physical chemistry, increase in temperature increases, like breaks obviously. When temperature increases, the bonds begin to break. Hydrogen bonds begin to break. All manner of bonds begin to break. Likewise in your NMR spectrum. If your sample is gotten at an increased temperature, it can affect the location where your sample is going to pick from, because at increased temperature, probably those hydrogen bonds which were formed are broken, and once they are broken, your sample cannot begin to pick at a much higher upfield state than when if they were broken and then they become picked at a very downfield state. The next thing we have on board is what they call the inductive effect. And usually now, the inductive effect is the most common and the most well-observed effect in an NMR spectrum, because inductive effect are split into two. They are based on two groups. They are split into two. They have the positive inductive effects and you have the negative inductive effects. Positive inductive effects are obtained when compounds or atoms or nuclei which have electron donating tendencies are in your sample. Then negative inductive effects are gotten when compounds with electron withdrawing effects are in your sample. So positive inductive effect is for electron donating groups, and the negative inductive effect is for electron withdrawing groups. And as a science student, I believe, well, it took me a while before I got to know what these things was, but I would say that electron donating groups are people that easily give out electrons. Examples is like your methyl groups, your nitro amino groups. They easily give out electrons. Nitro group is because it has a lone pair. The methyl group is because carbon is always available to bond anytime, anywhere, and is willing to share to form a covalent bond. But when you have electron withdrawing groups like the heavily oxidizing agents, hey, like the halogens, oxygen, and its family members, like men and brethren, what you would get, they would suck and they will drag the electrons to their side, increasing their own electron density, then decreasing the electron density of the other party involved. And once you are decreasing the electron density of probably a proton that is bonded to it, it becomes shielded. And once it is shielded, it will peak at a much higher frequency. Do you guys get it? So let us move on to the next part. Just like we said, remember, you are going to mix your sample with TMS, tetramethylsilane, your internal standard of what's interest. So as a scientist, if you remember, when you're doing back titration, you don't just titrate directly. You have to use a particular element which are going to minus or subtract the value from. Likewise in this place too. Now we'll be doing a comparison called a chemical shift. So now NMR results are represented in chemical shift. So this line, this horizontal line, talks about the different chemical shift of different like atoms on the sample. And remember, we're dealing with one hydrogen NMR, one H NMR. I'd like to say that one H NMR is like literally the most common NMR there is, because almost every substance on this earth that has hydrogen has the 1H hydrogen. So because it is very abundant, it is very sensitive. And I'd like to say that hydrogens in the 1H NMR don't live singly. They live in environments. Just like how microorganisms tend to live in colonies, hydrogens live in chemical environments. So it will be helping us, it will be helping you to know how we can have more than like a high amount of hydrogens, but then you'll be seeing very small peaks on your NMR spectrum. So a chemical shift is the difference in parts per million between the resonance frequency of your proton, of your sample proton, and that of tetramethylsilane. So the chemical shift is just the difference, the ratio between the resonance frequency of your proton of interest and the protons of tetramethylsilane. You know what tetramethylsilane will absorb at. It will absorb at a very upfield state. But then your proton of interest may or may not absorb at that particular height. So that ratio between where your sample peaked and where your TMS peaked, that ratio is called the chemical shift. And it is a delta scale, and then also it is measured in parts per million, because your sample usually is peaking at a very small like frequency in hertz, but then TMS is peaking at a very high frequency in megahertz. And if you remember, anything mega is times 10 raised per 6, so it's like m just regular hertz like this over megahertz. Obviously hertz will cancel hertz out, and what will be left with is what? 1 over what? 1 times 10 raised power 6. So when you're having 10 raised power minus 6 in this point, your sample can be represented in ppm, because a million is 10 million, understand? So moving on, I'd like to talk about like this spectrum. So this is like a very common NMR spectrum, and the sample that we have here is this is methanol, this is methyl group and alcohol group, this is methanol. And so on this side, talk about the peaks and how their heights, and then on the x-axis or on the horizontal axis, talk about the upfield and downfield effect. So now, like we said, hydrogens live in what? Chemical environment. You have the hydrogen. This one is beside an oxygen here. This one is beside a carbon. If you remember, one of the factors affecting the NMR spectrum is your inductive effect. And inductive effect is based on electron donating or electron withdrawing groups. In this very sweet structure here, we have an electron withdrawing group here, which is the oxygen. So whoever the oxygen will be bound to, the oxygen will want to de-shield that particular proton and then cause that particular proton to peak at a much lower frequency or magnetic field. That's what we have here. Remember, wherever, like we said, the 0 point is the most upfield point and it is the most shielded. Example, tetramethylsilane. Then the last point, which is 10, is the most downfield point, which is what? Your least value. So now oxygen comes here now to de-shield this hydrogen of interest here. That is why this hydrogen of interest cannot peak at the other points where the other hydrogen should peak. Oxygen will drag, because it has de-shielded this particular hydrogen, it will drag it down. To drag it towards downfield. It will de-shield it and then make it to absorb at a much lower frequency, but then at a much higher numerical value. So this particular hydrogen here, or this particular proton, is less shielded due to the oxygen, and then it peaks at a downfield effect closer to the 10. And this is what they call an example of an inductive effect. But then the rest of your hydrogens here, which are the same, which are attached to the same compound carbon, which usually live in the same chemical environment, they will peak at a much higher field. They're not really so directly attached, affected by this oxygen of interest. They will peak at a much higher field. And since oxygen is not there to block, to shield the electrons, they will be more shielded, they will peak at a much higher field, and they will be called in the off-field category. I don't know if you understand this. I really hope you do. So with this now, you have, in this case now, you're having 4 different like protons, but then you can still need 2 peaks. And this is because hydrogens live in what? Chemical environments. When we'll be talking about carbon NMR, you'll see that carbons don't live in chemical environments. Only hydrogen atoms get to live in chemical environments. So if you have similar groups of hydrogen atoms that live in same chemical environments, they will peak as one peak. And that's the reason why TMS, tetramethyl the hydrogen groups or the protons that live in the same chemical environment, they will peak. You can see it differently a very, very small peak when there are actually 12 hydrogen atoms on a TMS. But because they live in the same chemical environment, you just see them at the edge of the plate in one peak. You don't see them having 12 different peaks. No. You see them in one peak. And I'd like to say something about the height of the peak. The height of the peak is indicative of the amount of hydrogen atoms in that environment. This one that has only 1, you can see that the peak is shorter. While this one that has 3, the methyl group, has a much higher peak. Pardon my very sweet drawings, but like you can see that it is peaking at the height is very tall because there are 3 hydrogen atoms compared to this one that is just only 1 hydrogen atom for it. So thank you. I really hope you understand. This is how a basic NMR spectrum, like this is how they read the different spectrums on it. Thank you. So as we have seen with our methanol example, we've seen how oxygen with its negative inductive effects was able to de-shield 1 proton and moved it downfield. So with this now, it can help you to determine if your sample probably has like an oxygen or a group, an electron withdrawing group. You will notice that in the NMR spectrum of your sample, you'll be noticing that some protons will be de-shielded, some protons will be shifted towards the downfield axis, while some will be left towards the off-field axis. This all depends on whether there's a presence of inductive effects or the presence of positive or negative inductive effects. Although there are other factors that can be responsible for your eventual NMR spectrum. So I would like to show us a table of the typical value of our chemical shift. Just like we said, the chemical shift is the ratio of the resonance frequency of your observed proton and the protons of TMS. So now we know that we said that chemical shifts are represented in tau values. The tau values, that ratio, it is a number, and that number can be called a tau value number. So whenever you hear the tau value, just know it's all talking about the chemical shift. And just like we said, the ratio between your proton of interest and the TMS protons, your internal standard protons. So now, in this case now, where you have like a terminal alkyne, this is an alkane group at the edge, that is the CH string. You will notice that with time, with practice, you'll notice that the tau value is actually giving you 0.9. You can see it is very close to TMS. TMS is 0, and then this one is what? 0.9, because there's literally no form of inductive effect that really happens to it. If any inductive effect is a positive one, because carbon gets to give to these hydrogens, shielding them very well, and then you'll find yourself in the most off-field region, where very close to TMS, which is 0. Moving on to this next example, now you have a non-terminal alkane group. This is CH2, and then there's another extra bond there. This type is giving you a tau value of 1.3. It's still very close to your 0.9 because this is just a carbon that is trying to give electrons to your hydrogens that you have here. The next part you have now is your alkyne group, where you're having 2 carbons bounded together, and then you have a hydrogen group at the end, a hydrogen or a proton at the end of the day. Obviously, the hydrogen is not directly affected by the alkyne group, but it is indirectly affected because of this whole unsaturation and anisotropy that we talked about. This unsaturation now can make this hydrogen to be a bit de-shielded, and then make it to peak at a much lower frequency, and then give it a higher numerical number. So don't forget, it will peak at a much lower frequency, but then it will give it a higher numerical number. Then the next group we have here is the aromatic group. So this pH stands for phenyl, and so phenyl bonded to H gives a benzene ring. And because, like we said, on saturation, or the anisotropy that you can observe in benzene, that the electrons, the localized pi electrons, since they are not attracted to the the field that you now introduce, they will leave their piece of primary assignment and then start facing that field. The protons, then the carbon protons, the hydrogen protons become shielded, and with that they get to peak at a very far distance of what, 7.2. This anisotropy is what accounts for benzene rings. It accounts for all manner of aromatics, because in the aromatic ring regularly there's no form of electronegativity. It's just carbon and hydrogen. So what is making the regular carbon and hydrogen, which will just give you 0.9, why would this have to give you 7.2? It's all because of what? Anisotropy, because of the pi bonds. The next thing that you have here is the aldehyde group. You're having carbon that is bonded to a lot of things. This hydrogen is bonded to carbon, which is bonded to oxygen. This whole complex setup can make the hydrogens to peak at a very downfield point, which is what, 9 to 10. And then the next thing you have is your double bonded group, your alkene group, and you're having it peaking at a point of 5 to 6. So you can see with these different particular structures, these different particular like structures and structures in the layout, you can see that different hydrogens, different protons get to peak at different frequencies, either downfield or upfield. So let's not forget the keywords: chemical shifts, the downfield, the upfield, the inductive effects, your NMR spectrum, your radio frequency transmitter, and your nuclear magnetic resonance. Don't forget, it all happens because of what? Resonance. It all happens because they get to agree at a particular point of interest. Thank you, and see you in our next video where you can talk about carbon NMR and other amazing applications of NMR spectroscopy. Thanks and bye.